In the previous video we looked at the concept of electric current. There's another concept that we need to deal with that's just as important. That's potential difference and EMF. They're sort of two sides of the same coin, so we'll talk about both of those as we go through this video. Now, in order for an electric current to flow, we need to provide some impetus for the charges to move, and so an electric current can only flow through a conductor when there is a battery or a power supply that's going to cause those charges to move. And when we're talking about a power supply, that could be something like a power pack that we might see in the science lab, or it could simply just be plugging into the power point in the wall. So whatever the source of electricity is that is being used. Now, the reason why we see an electric current start to flow is because this establishes an electric field in the conductor itself. So with the electric field inside the conductor, and we saw that a diagram of that in the previous video, it means that there is a force that's going to act on the charges within the conductor and cause them to move. And the way that that's going to be established is that it's going to be from the positive terminal of the battery or power supply through the conductor itself to the negative terminal. So that's the direction of the electric field, and as a result, as I said, that means that the charge carriers are going to experience a force, and that's going to cause the charge carriers to move. Now, there's a really important point to note here about this movement of charge carriers, and it deals with how we're going to look at current moving through the rest of this unit. And there are two terms to be familiar with here. The first is electron flow, and it's the one that makes most sense. It's simply the direction that electrons move, and that's always going to be from negative to positive. So the negative charges on electrons will be repelled from the negative and attracted to the positive terminal, and so that's the direction that the electrons move. Unfortunately, when all of these concepts of electricity were first being discovered, they didn't know much about electrons, and so they figured that whatever it was that was moving must have been some positive charge, and so conventional current is the current that we're actually going to be using, and that flows from positive to negative. Now, there isn't actually anything that moves from positive to negative. We imagine that it's positive charges, but we know that there are no moving positive charges in a conductor, and so this idea of conventional current is one that sort of started with the development of understanding of electricity, and unfortunately it's stuck, and so that's the way that we'll go through and analyse the circuits. Having said that, it doesn't really affect anything all that significantly. There's only one scenario that I can think of where it makes more sense to talk about electron flow, and that's in semiconductor components, but we don't really need to cover those in any detail in SL, and so it doesn't really matter whether we're talking about electron flow or conventional current, but just be aware that when we're talking about conventional current, we're always going to move from positive to negative. Now, due to their position in that electric field, charge carriers are going to have electric potential energy. Now, the idea of electric potential energy is a really important one to try and wrap your mind around. The idea is not too dissimilar to gravitational potential energy. So in gravitational potential energy, if you lift a mass and raise it against the gravitational field, that mass is going to gain gravitational potential energy. So in a similar way, when charge carriers are moved against an electric field, they're going to have electric potential energy. So that it means then that the charges don't have energy within them. It's that the charge in the position that it is in within the electric field means that it is going to store energy. As those charge carriers then move through a circuit, and we'll deal with circuits in more detail in topic 5.2, but we'll just mention it here to help explain this concept of potential difference. They're going to move through circuit components, and some of those circuit components that we'll look at are things like a lamp. We can even consider a battery as being a circuit component. So as they move through those circuit components, the electric potential energy is going to be converted. So it's going to be converted either from or to other forms of energy. And if we think about those two circuit components that we've already identified, we would say that it's converted to light energy in a lamp, and it's converted from chemical potential energy in a battery. So we need to be aware of both of those situations, so whether it's being converted from or to, and what the form is that it's being converted from or to as well. Now, the amount of energy converted per coulomb of charge, so we're now looking at a certain quantity of charge and how much energy is being converted as that charge moves through a circuit component. That's a particular quantity that you've probably heard of before, or at least heard the term. It's commonly known as voltage. So as we have a whole lot of charge moving through a component, it's going to convert, say, electrical energy to light energy, and so we talk about how much energy per coulomb, and we talk about what voltage that light bulb might be. The equation then is fairly straightforward. V is equal to W over Q, and that is one that's in the data booklet. To identify what the terms are there, we've already stated that V is the voltage, and just to be a little bit confusing, when we're talking about voltage, it's measured in volts, and the symbol for volts is capital V. So you might see in some situations that the voltage of a battery is 9 volts, so V is equal to 9V. So it looks a bit confusing, but just be aware that when V is by itself, it means the voltage. When it's being used as a unit, it's volts. W is the energy that's being converted, and energy, as we know, is measured in joules. And Q is the total charge that's involved in that conversion. So all of the charge that's moving through the circuit component that's causing the energy to be converted, and that's measured in coulombs. Now, that term voltage is a fairly general term, and we need to be a little bit more specific about whether or not the energy is being converted to electric potential energy, or whether it's being converted from electric potential energy. And that means we've got two categories that we can classify voltages into, and those two categories are the two terms that we had right at the beginning. The first one being potential difference, and so that's where electric potential energy is converted into other forms. So you would talk about the potential difference across a light bulb, for example. There are lots of other situations where electric potential energy can be converted to other forms, and we'll have a look at the example of resistors in a fair bit of detail in the next few topics. And then the alternative to that is electromotive force. and that usually gets shortened to EMF. Be careful here, while it has the word force in it, it's not actually a force, it's a voltage. So it's the force that causes the motion of electrons, if you want to think of it that way, but it's really just a voltage where other forms of energy are converted to electric potential energy. So there's the two types of voltage that we need to be aware of, and need to be clear on the usage of those words to make sure that if you're talking about where energy is being used, then it's a potential difference. If you're talking about where energy is being supplied, like a battery, then you'd be talking about an electromotive force or an EMF. So for a potential difference, you can think of it as being that the voltage goes down, whereas for an EMF, the voltage goes up. Now we're going to take a step backwards here for a second to identify that the concept of voltage doesn't just apply to currents, it also applies in electrostatics. It's really just a matter of moving charges through electric fields, and so given that with electrostatics we have electric fields surrounding charges, then we can move charges through those electric fields. So for example, let's imagine that we have a charge positioned here, we'll call it capital Q, and it's positive. So we know that the field lines around that charge are going to be directed away from it. And we're going to consider 2 points in that field. And those 2 points will be, say, this point here, we'll call it point B, and out here is point A. And if we have a charge of plus Q at A, energy would be needed to move the charge, and that's Q, from A to B. So because energy is being used, there's a conversion of energy from some other form into electric potential energy in this case. We can calculate the voltage between those 2 points, and I'm going to use the same equation that we saw before, except we're going to have a little bit of an added extra by indicating the direction that we're looking at. That's going to be given by the equation VAB. So we're looking at the voltage from A to B. So that's still going to be equal to that equation W on Q. W here is the energy that we're putting into the system, so moving the charge from A to B, so we're doing work, we're putting energy into it, and Q is the size of the charge that we're moving. One last point then is about the units of energy that we can use. And the unit of a joule is fairly large, but if we consider the charge carriers themselves, they're quite small charges. So when we're dealing with that quantity of Q, it's usually going to be a whole lot of charge that's moved past a point in the circuit rather than an individual charge. If we're looking at energy on very small scales, so if we're talking about an individual electron or an individual small charge of some very small quantity, we can use the units of electron volts, and the symbol for that is E with a capital V. Be careful here, again, it's got the term volt in it, but it's got nothing to do with voltage. It's a unit of energy, and it is the energy required to move an electron, hence the term electron in it, the energy required to move an electron through a voltage of 1 volt. So if we look at the definition, we can use that equation again, V is equal to W on Q. We're trying to figure out what the amount of energy is, so we'll rearrange that to write that W is equal to QV. Now the charge on an electron is negative 1.60 by 10 to the negative 19 coulombs, which is in the data booklet, and we're moving it through a voltage of 1 volt. So that gives us an answer of negative 1.60 by 10 to the negative 19 joules. Now the negative out the front is just the fact that the charge itself is negative, so we can conclude from that then that 1 electron volt is equal to 1.60 by 10 to the negative 19 joules, so just ignoring that negative. Now that quantity isn't actually in the data booklet, but you'll notice that the size of 1 electron volt in joules, that number is the same as the size of the charge on an electron. So you shouldn't really need to worry too much about that definition. It's just that same number, 1.60 by 10 to the negative 19. As I said earlier, we'll be moving on to electric circuits in the next topic, 5.2, but we'll still be using these ideas of current, voltage, potential difference EMF, so make sure you've got them well and truly under control.